The supernova will practice. Yeah, so.
Mike, could you push play on that?
On the music?
Yes, please.
If you want that louder, you might use the desktop sound.
The desktop sound.
Yeah, over.
JD, do you want it louder?
Yeah, if you crank that up, it'll crank up pretty loud.
Okay.
Yeah, he just said, what he said was, he was chopping the,
Let's share.
he was chopping
Share.
away,
Full
going
family. Share full screen.
then he wondered,
Okay. Do we want to turn that up a little?
We're chasing stars that burn so bright. In cosmic winds, they light the night. Type 1 lids, pure ignite. Two white dwarfs dance, then take flight. Boom, boom, boom goes the stellar show. Supernova sparks, let's watch it glow. Every type a tale to know. Exploding hearts, the skies bestow. Type 2 comes from massive might. A dying star's dramatic fight. Its core collapses, out it blows. A nebula forms where it used to pose. Neutron stars and black holes form. From chaos comes a cosmic norm. These remnants whisper through the void. Creation birth where stars destroy. Boom, boom goes the stellar show. Supernova sparks, let's watch it glow. Every
Just in case.
All right, we shall begin with one more
Now.
minor.
Answer is that?
Yeah, right.
Okay, as long as they know how to use it.
Yeah, so how do I?
With one more
So-
minor
Forward,
thing.
backward. This is a green laser.
What did you do? We've got the video. I sent the video.
You did?
I sent the video to Willem. He confirmed receipt. Okay. Yeah, I don't know either. All right, let's begin. You would be so kind, Mr. Nassir.
Sorry, I gotta get that. Hi everyone. Welcome to our High Star presentations for 2026. I'm Mike Nasser. I'm an old friend and colleague. Well, that's good talk to you. Do I need to talk to the internet? Okay, I think I need to talk to the internet. So this microphone here goes out over YouTube, and that one is for the room. Okay. Okay. So hi everyone, my name is Mike Nasser. I'm an instructor in physics and astronomy at UH Manoa. I was able to come out for the day and help with High Star 2026. I'm actually an old colleague of J.D. Armstrong's. Together we founded High Star way back in 2007. So it's very exciting to see it continue to this day. So unfortunately, I've only just met the students today, but I'm going to do my best to try and do a little introduction for them. Our first presentation is going to be on classification of supernovae. The team members are Noel Ramirez, who is not here today, but do you have an audio recording of him, or?
Yeah, I'm not
Okay.
sure.
Pardon me, I've heard, yeah.
I'm not sure what it is though.
Okay. So, but Noel did contribute to the research and the presentation. And then over here on your right is Landon Kuloloyo, and he's a first-timer in High Star. And your left is Lexi Lombardi, and she is a two-time returner. So this is her third summer with High Star. Okay, take it away.
So you have to go from the start. Do you want me to do it? Or do you want to do it? Me?
Go ahead.
Okay, so I'm Lexi, and this is our Supernova Classification project. Why is it not working? It's just-
Oh, that's not.
Oh.
Maybe it got
Oh.
switched off.
No.
When it fell on the ground.
And that also helps if we plug the dongle in.
It is plugged in. Great, it's
Oh,
working now.
okay.
Oh, yeah, thank you.
Great.
So first off, we're going to give you guys a little bit of background. This is a typical supernova classification chart. The main difference between type 1 and type 2 supernova is that type 2 supernovae have hydrogen and type 1 don't. And then from there on, it gets a little bit more complex, and it just basically goes off of what elements we can see inside of them. So the most common ones you'll see are supernova type 1A, B, C, and then the most common for type 2s are type 2B and just what we call type 2. Very creative naming system. So this is a spectra. On the x-axis or the bottom, you'll see different wavelengths, and on the y, there's typically flux. And yeah, so this is the first supernova that we looked at. This is kind of when we were just learning about spectra lines and how to look for them. So this is supernova 2026 NZW. We have 3 different elements here. So we have hydrogen, helium, and silicon, which gives us a hint that it's likely a type 1A. Type 1As will always also see silicon at around the 6,000 angstrom mark. Here's another one. This one just says hydrogen and helium. There's certain marks where we will see certain elements, which is also really interesting to me. Those certain marks are pretty much always there, so that's one of the main ways we'd help to classify them. And then I'm not going to get too much into this, but there are two different types of core collapse. So there's core collapse supernovae and thermonuclear supernovae. Basically, it's the way that they supernovae in on themselves. Thermonuclear are when a binary, so 2 stars, a star system of 2 or more stars, smaller stars have a strong binary interaction, so they're interacting with each other. And then a white dwarf binary forms So that's just another interaction, and in the end, we typically get a type 1a supernova. Actually, it's only type 1a supernova. And then core collapse are more massive stars, and that's a whole nother process. It's basically when they burn up all of their elements up to the core, and they can no longer support themselves, so they just explode, which is a typical thing for supernovae. And that can happen typically more in younger galaxies because there are more elements available. So this is one of the animations. I believe this is a thermonuclear supernova. And then that's a core collapse. They're both very violent interactions. Again, we have old galaxies, which are typically kind of almost look like just smudges. That's because most of their more massive stars have burned and turned into supernovae or are just gone. Young galaxies are the really pretty ones we like to see. That is a spiral galaxy right there. And the reason why we have a lot more supernovae in those a lot of time is because they have more massive stars that have a greater mass.
Okay. This is the Doppler effect, explained by me, of course, Landon Kulaloyo. So instead of light, we're going to compare it to sound from a car. When a car comes toward you, the sound gets, of course, louder and the pitch gets higher. And when the car goes away from you, the sound of the car gets quieter and the pitch gets lower. This is videos of cars going away from you. They go vroom. How we figured out what our supernovae was made out of. So first, we took a spectra of a type 1a supernovae, and then I chose silicon because usually and always, type 1 supernovae will usually have silicon. I chose silicon because it should have it. So when I chose silicon, it stayed neutral, and when I turned it into 10,000 kilometers a second, the lines changed from a spike to a dip. When I chose iron for my random element to see if it's in this supernovae, I first started off with 0 kilometers a second, and then I moved on to 10,000 to see if it matched up with the silicon at 10,000 as well. And it sure did line with a dip. So that means it should have iron. And communication matters. I communicated with my teacher, Mr. Haagen-Dazs, and he let me have a lot of fun, and he was a great teacher. Thank you, Mr. Haagen-Dazs. Okay, you go.
Yeah, so that was the first part of our project, was to classify them. Next, we wanted to make something where we could easily see the different types and their spectra all next to each other. And originally, we were using a different database in order to grab our information. Then we ended up switching to the transient name server. This is a server where most, I would say, well, not most, but a good portion of the supernovae reported here have not been classified yet. This is one that I was working on, so there is a spectra later in the final graph from this. It actually did end up being classified. I looked at it again yesterday. And it's actually a really helpful website. This is what we used. So at the top, you'll see that there is the supernova name, and then RA and DEC in the top left, which is basically how astronomers use coordinates in the sky. You can't exactly just point at a star and say that's where it is. Not everyone will have that. So it's a very precise system of coordinates. And then right next to that, you'll see the type it is, and then the redshift or blue shift, which is what Landon was talking about, the Doppler effect. It's so when something's blue shifted, it's moving towards you, and when it's red shifted, it's moving away. And then you also have a discovery report and classification report. Those are if you really want to kind of dig in deeper to some of the attributes. And below, on the bottom half, below that white line, you can see who actually reported it or found the supernovae. You also see the discovery date, if it's public or not, and the magnitude, which is essentially how bright the supernova is. So this one had a magnitude of about 17.3, which isn't super bright, but it's not the most faint thing ever. And on the same page, you'll also see images and spectra. So this is an image of that supernova that we were just talking about. And it's probably a little bit hard to see, but that purple crosshair up there is where the supernova was detected. You typically want to see if it's bright, if it's within kind of a host galaxy, and when it was kind of discovered to get you a better idea. And then you also see another spectra. So again, on the x-axis, we have the wavelength, y-axis, we have how bright it is. And in this one, I believe those two lines are, since it was a type 1a, that line around 6,000, so that green line is silicon, and then the more blue/purple lines are iron. I believe they're iron, yeah. So once we started going through all of our data, we ended up writing a lot of Python code, which is a long and boring process, I'm gonna be honest. But it was still very fun because I learned how to program. But this is kind of just a short snippet of our code. It gives all the details for the graphs, and this was actually a really fun kind of process because I learned a lot. A lot of the data that was collected, sometimes they're on different scales, so you need to get them all on one scale, so it's a bit of math. And another thing is you can play with the offset between them to get them more separated on a graph. And these are essentially the 6 main types on one graph, just so you can see. And you can see there's definitely some similarities and differences, which should make sense. And my favorite thing about this one is if you look at the type 2, just the type 2 supernova, that's the purple one on the top there, it has these really strong lines while everything else is kind of more smooth. This is because, or the reason what we think this is, the reason what we think this is we think it's a supernova ejecting material or ejecting certain elements, and that's actually an ongoing field of research right now. And yeah, we basically did some analysis on this, we agreed with what the experts found, that they were indeed these type of supernovae. And the next thing that I started getting curious about is how common each type is. So these are the 6 most common types of supernovae. You have 1A, 1B, 1C, 2, 2B, and others. So I actually found that the most common one was supernova 1A. It's about 65%. The next common supernova is just the type 2, that's 16%. And then supernova type B, 1C, and 1B are all about 2%, so they're much less common. And then there are a ton of different classifications that get super specific for supernovae. I'd say there's at least 15 different types. Those other ones are about 13%. And our friend Raina, even though she couldn't be here today, she wanted to be here with us. And we were talking, this side that was originally called Communicate with Raina. And we were laughing, we're like, what if we kept this in for the presentation? And she's like, I'm down for that. And in the end, I told her, put whatever you want to put. And she said, make sure to tell JD he's the GOAT. Thank you. Any questions?
Why did you guys choose supernovae for your presentation?
Please repeat the question for the streaming audience.
Okay. So the question was, why did we choose supernovae for our project? Personally, for me, I always just find them really interesting, especially since they're typically pretty far away from us, and I find it really amazing how we can get all this information despite never being able to directly touch it or be able to take a sample. And then Landon, do you want to give your answer?
So the reason why
Here, come here.
supernovae was because the reason why we chose supernovae because when I can't really answer this.
Why did you choose it?
The reason why I chose it was because I was really curious when Mr. Haagen-Dazs kept on convincing me that kabooms were really interesting to see from stars. And I said to Mr. Haagen-Dazs, I like kabooms, so I chose supernovae.
Any other questions? All right.
Thank you.
Galaxies, you're on deck. You should be up here. Come on up.
Great. I forgot to acknowledge Willem. So Willem, your last name is Hogendam? Yeah. There, very good. Okay. So, but it looks a little like Haagen-Dazs, so that's why that became a thing. So Willem Hogendam is one of our graduate students at UH Manoa, and he was the mentor for that Supernova project. So, and he's been here all week. So thank you very much, Willem. And so our next group, and I'll just mention the mentor right now, our next group, the Galaxy Merger group, was mentored by Miranda Kong, who is also a graduate student at IFA Manoa, who's also been here all week. So thank you very much for your time and your energies. The Galaxy Merger group is all three of them are third-year high star returners. It's Chelsea Miguel, James Anchetta, and Lingel Pagel. As soon as it's ready to go, take it away. Still time, yeah, there's still some sound.
Oh, is this good?
And you'll still need to speak loud too. This part of the microphone goes out over the internet. That's what you can also please go ahead. Where's the field of view? Forward. Yeah, back your way. Great. Yeah. Try just clicking it one time and see if it works. I'm sure it works. Great. Okay. Go.
Okay.
All right. All yours.
Oh, okay. Wait, I'm gonna wait for everyone to sit down. Okay, salutations everyone. My name is Lingel. This is James Anchetta. This is Chelsea Miguel. And we are the Galaxy Merger group. And our presentation is titled The Destruction of Galaxies. But before we start, this is what happens when two galaxies collide. Wow. Okay, so what exactly are galaxies? Galaxies are these massive systems in space that are made up of multiple stars, planets, and clouds of gas and dust. They are held together by gravity, and their diameters can be as long as like, millions of light years long. The different types of galaxies. Although galaxies are just systems in space, they can come in different types. And these different types they can take in different forms. The three main forms of galaxies are elliptical galaxies, spiral galaxies, and irregular galaxies. Elliptical galaxies are flat and round, just like plates in the sky, and they also have central bulges in the middle, and they are usually red because these elliptical galaxies usually consist of older stars, and older stars emit red light. So, we also have spiral galaxies. Spiral galaxies are quite similar to elliptical galaxies. The only difference is that they have arms. And these arms are made up of gas and dust. And these spiral galaxies can have 2 or more arms. They also have a central bulge in the middle and usually are the color blue because they are a mix of young and older stars. And their last type of galaxy are irregular galaxies. And I mean, while spiral and elliptical galaxies have a clear structure, irregular galaxies, they don't. They are usually these clumps and blots of stars, and they really have no clear structure to them, just clumps, basically. Well, they also have different types. Did you also know that galaxies can merge and collide with each other? We call these galaxy mergers, and this happens when 2 or more galaxies collide. Galaxy mergers take place when multiple galaxies are pulled together by gravity. They then start to pass around each other in this kind of galactic dance in the sky. And as they pass around, gas and dust are being pulled out and ripped apart. And they form these thin like strands of like trails of streams and tails. And as they begin to condense, the center bulge, two center bulges merge together, and then we have a merged galaxy.
So our overarching question for this project is, how do galaxy mergers affect galaxies' morphology, like their shape, and star formation of the resulting galaxy after merge?
Okay, so for our methodology, we first were introduced to Zooniverse, which was a crowdsourced or a people's opinion and classification source where people can classify different types of galaxies and as well as different types of galaxy mergers as well through different types of features. For example, for the spiral galaxy, they usually have a center bulge and multiple different arms, and for the elliptical galaxy, you would notice that it would have this sort of round ovalish and gassy shape. And so we used that crowdsourced data and downloaded it, and also used it with a sample with the SDSS photometry sky server data and merged them through different types and through the same morphology classifications with the data itself. So classifying them through different types of classes like spiral, elliptical, or merger from the crowdsourced or from the data collected from different types of people. And so you can see within the data itself, it's structured so that it shows us their specific type of object ID, and as well as the right extension and the declination within the data set. And so we used, in order to fully investigate and to test different types of galaxies, we used Google Colab and installed a library called Matplot Library and plotted the difference of different types of galaxies through the redness or the R band. And this is specifically on SDSS Sky Server, where they use photometry bands to measure the specific color that they could radiate, and using that to graph different types of plots.
So with that, with the data gathered from Galaxy Zoo, we generated two plots. So the first one we generated was this histogram. So what this histogram is, it shows the distribution of galaxies along a graph with the x-axis being color wavelengths, and the y-axis is density, or how intense this brightness is. So as you can see on the graph, signified by the blue, spiral galaxies are typically bluer because it has shorter wavelengths, and shorter light wavelengths result in higher energy wavelengths, and it appears bluer to the human eye. So for elliptical galaxies, which is the spike around the 1.0 mark, that means that it's redder, more red compared to the spiral galaxies. And in this scatter plot over here, this is again plotted by redness on the bottom on the x-axis, and redness magnitude on the y-axis, or how intense that redness is. So as we go to the left of the graph, it becomes less red, or consequently more blue. So we can see that as the red intensity goes down, or as galaxies become bluer, it's more often the spiral galaxies that are blue. As you can see, there's not many elliptical or merger galaxies down that low in the blue. Whereas as we go up, as it gets redder, but all three, elliptical, spirals, and mergers, they can all be red. Okay. Is that you?
Okay, so what we did do is get some collected galaxies from the SDSS sky server, and we classified them towards the timeline on how a galaxy merger happens or occurs. And since galaxy mergers occur through a duration of multiple millions to billions of years, it would be good to understand what is the process and what underlying conditions does the star merger go through. And so we can see from the post-collision or pre-starburst, it looks a little blue. And so once after the two galaxies, since they have so much potential, so much gravitational force already, once they collide within each other, those those forces are very chaotically changed, and so that kinetic energy from that galaxy is fundamentally permanently damaged. And so due to this, there's a lot of gas that gets shotted out, as the GIF suggests in the start of the slide. And due to that, there's an excess amount of gas remaining in the galaxy that gets bundled up and collides within each other, forming and basically becoming a nursery for blue and young stars. And so that's why for the starburst stage, we can see that most of the galaxies are very blue-shaped. And we can see from the other forms, we get eventually, once the collision happens, they merge and coalesce into one different type of galaxy. And this type of galaxy is called an elliptical galaxy because of the gas that was lost. And an elliptical galaxy is also defined by the onset of or needing gas within the galaxy itself. And so we can also see here, we can see emerging galaxies. Like Lingel said, there's a little bit of streams around there. And different types of the galaxies coalescing with each other. We can see more streams over here. And we can see at most of the final stages, when it coalesces into one nuclei, we can see it sort of looks like a binary star, or super close together. And slowly it turns into a red elliptical because they do not have this gas to form stars or to form heat. And so in essence, it turns more red because in photometry or in light terms, the more red the color is, the more cooler it is. And so it can't reproduce or get more stars in there. Oh, and
Wait, go back. Go back. Go right. Your other right.
show. Oh. Okay.
So one of the images didn't load, sadly. But in conclusion, galaxies change throughout their lifetimes. Whether they change, whether they start out as blue spirals and then slowly lose energy, become redder, and have less star formation, or they merge. They are high in energy, and then in the merging, they shoot out lots of gas, and then after merging, maybe they don't have enough gas to create star formation, to form stars. So galaxies can change in different ways and have different lifetimes, or different timelines depending on what happens to them. So for future work, we would like to simulate reactions with the Andromeda Galaxy, which would help us understand physics at a cosmic level, and then have more precise merger classifications to separate and better classify these galaxies. So thank you. Any questions?
Did you notice which galaxy tends to have a longer life?
Right, yes. Okay. So red elliptical galaxies. Oh, sorry. So you asked if we found out which galaxies tend to have a longer life. Yes, okay. So red galaxies tend to have longer lifespans because blue galaxies, as we said before, they're in the starburst phase. It has high star formation and such. But after a starburst phase, like post-starburst, all of that heated gas that hot gas in the environment of the galaxy, it's unable to create stars because stars form from cool and dense gas. So it's usually the red elliptical galaxies that are able to form new stars and have longer lives. Yes, Landon.
Why did you choose galaxy mergers besides just galaxies?
You want to answer?
No, we can all answer.
Okay. Okay, I can start. So you asked why we chose galaxy mergers instead of galaxies. It's just cool. Imagine having one galaxy, but now you have two galaxies, and they're merging. So I think seeing how not only got to see how galaxies act independently, but how they act in relation to other galaxies. I think that was very interesting, how they interact with each other.
For me, I kind of chose galaxy mergers because I was kind of interested in specifically how the interactions of black holes had with stars. It was basically ripping the stars off. So I was making that correlation with gravity mergers that it could possibly, what would happen with a supermassive black hole inside the galaxy and how does that interact with each other?
For my answer, I think galaxies as a whole are just like really interesting. I did a project last year. I did High Star last year, and I'm pretty sure I joined the Galaxy group for it. We were focusing on like determining ages for galaxies because besides the fact that they can be merged, you can also use them to basically retell, how the universe was formed, basically. Because as the universe expands, these wavelengths of light start to become more elongated, right? And they become redder. So these galaxies that are redder mean they are more older. So I kind of just like that. I like to know how the universe was formed. It's expanding a lot, and I think that's really cool. Yeah.
Great.
Oh wait. One more question. Sorry, could you say that again?
Is that a test question, or are you asking out of because you're not sure yourself? I'm not sure. Oh, okay. It might not have been part of their project.
So your question was, how are we able to detect supermassive black holes at the... Mhm. How to detect if there is a black hole at the center of the galaxy? I'm not sure.
Encountered that in your work? No.
I don't think we looked specifically at black holes. We just looked at the surrounding gas that is visible in the galaxies. But I think that'd be an interesting project to continue off of too.
I think I'll just try to I don't think it's like an educated guess, but the accretion disk, we're able to mostly see black holes because of the accretion disk, because of the specific types of material. These material are slowly drifting away, it can look like from an observer, it looks like they're slowly going into the black hole for like millions and millions of years, but that's, it takes fundamentally a lot of time because eventually, it depends on like the material. If you're a human, you might get spaghettified, but it takes a long process. So I think due to the light of the accretion disk, and I think as well as emission lines, that was an educated guess though.
It's good. That's a good guess. That is one of the ways that they're observed.
Oh, okay.
Yeah, emission from the accretion disk, the ultra-hot accretion disk emits X-rays. I know, the internet doesn't use this. Okay, so there's jets, the outflows from the black hole are observed in jets. You guys, the Nobel Prize about 3 or 4 years ago was given because they observed stars very close to the Milky Way's black hole orbiting on like a 20-year time scale. They plotted those, they got the mass of the black hole as 4 million solar masses. So it's all these are indirect methods, right? It's impossible to just basically look right at the black hole and see this thing glowing with a signature inside the black hole. Yeah, sure. Oh, and then gravity waves. So when 2 of these black holes actually merge, then it creates this huge gravity wave explosion. So things like LIGO are just starting. We only have like 10 years of data on that, but that's also potentially a way to do it. Although I don't know if any supermassive black hole mergers have been observed yet. It's all been things in the order of tens of solar masses merging, right? Willem, Amanda, does that sound about right? Yeah. So in theory, if a double supermassive black hole were to merge, we would see this massive gravitational wave event. But that hasn't been observed yet. We've only seen ones that are much smaller. Okay, so this is the next one. Great. Let's thank our merger team. I was really proud of
Okay, go for the final.
Okay, sorry, internet. If any of you would like to know more about black holes, please Google that. Okay, so I wanted to say,
exoplanets in a stellar romance, orbiting stars in a celestial trance, mysteries so deep they don't stand a chance.
And then
Big fat exoplanets spinning so wide,
final
hiding in the dark where the secrets reside. Galaxies are watching, they can't be denied. Big fat exoplanets on a stellar ride.
Bouncer.
Like kings bleed out in the night. Color so vivid, it's a galactic delight. Gas giants flexing with the glow so bright.
So everyone, our third and final research team this summer is the Exoplanet research team. They were mentored by J.D. Armstrong himself. We have 2 first-time high-star participants, Lucas Garland and Neil Vyman, and a third-year high-star participant, Emma Agkolakol. And Emma is going to, I think, start us off. Okay, great. No, I can help hide that for you. You want to hide the?
No, we're trying to find the slides.
Oh, the slides.
This is not our slides, this is the old one.
Let me see if I can help. Yeah, it should be right here. Right. Present. Okay, and we also have to hide this puppy down here. Okay. Is that everything?
All right. Hi, everyone. I'm Emma. That's Lucas, and this is Neil. And our project title is Confirming the Existence of Exoplanets with Transits. So, first of all, what... Thing not working. Can you go ahead? Okay. So, what are exoplanets? Exoplanets are planets that are found outside of our solar system that do not orbit our sun. And the reason why they are super important to study is because using the research we can get from them, we can discover the origins of the universe and also see if we are truly alone and see if life exists on other planets.
Okay, so how are exoplanets discovered? There are several different ways. I'll go quickly into some of them. There's direct observation, which basically you observe the system, the host star plus the planets, and you try to block out the host star's light to see the planets. There's the Doppler effect, which uses gravitational properties as well as light waves to help detect exoplanets. There's also proper motion, which astronomers basically use, or they see the wobble in a host star to see if there's an exoplanet there. And there's also microlensing, which uses gravitational waves bending the light around a host star to detect the exoplanet. And then there's the transit method, which we will go into a little bit more deeply here.
The transit method is the method used primarily by astronomers. It's been used to discover almost over 80% of the known exoplanets. The number right now confirmed by NASA is around 2,900 or 6,900 exoplanets. The transit method involves measuring the light that is lost as a planet, as a candidate planet crosses in front of its star. That's measured on what's called a light curve, which is a graph of light against time. So as that candidate planet moves in front of its host star, a little bit of light is lost, and it can be measured whether or not it is an actual planet.
So while doing this project, there are a couple of very important things we need to look out for when trying to detect exoplanets. The first of the two being red ascension and declination, essentially where it is in the sky. There's also magnitude of the star, or the brightness of it. There's orbital period, which we were deeply concerned about because we wanted to get candidates where they would transit during the duration of the week. And lastly, transit depth, how much light was lost during the transit so we would be able to see it clearly.
So for finding these exoplanets, we use a program called ExoFOP, which basically we filter out different requirements. As you can see, the right ascension, declination, period, duration, the depth, and the planet radius. These, we see here the name starts with TOI and then a number. TOI stands for target of interest, and there's many different host stars, so we use a number to signify which star we're talking about.
Using ExoFOP was just the first step of measuring or looking for these exoplanets. What we did with the information that we found, with the coordinates and all of that, was we programmed it into what's called the LCO, or the Los Cumbres Observatory. The Los Cumbres Observatory is a series of over 20 telescopes over the world. I believe the number is 27, actually, where scientists are able to program in their observations based on specific coordinates in the sky and get detailed observations by different sizes of very powerful telescopes.
So once we got all of our image observations, we then used a program known as AstroImageJ, which allowed us to import all of our images and place apertures on our host star. And the cool thing about AstroImageJ is that once you place the aperture, it'll graph your light curve for you, so we didn't have to do it manually. And with the light curves, we decided to see if we caught the two different transits we tried to observe.
The first candidate that we found was TOI 5848. TOI 5848 had very promising results. It had a depth. It had a very strong depth, which means it blocked out most of the light. It also had a pretty decent period, so it could be observed fairly quickly. It also did not have too bad of a magnitude. So all of these lined up. It was in the right spot in the sky. Now what made it a little difficult to observe was it had a 50% uncertainty. What that means is that there is a period of 12 hours that it could be uncertain. When you go on ExoFOP, you can see the event midpoint. You're given when it's most likely to be seen, when it's like most visible. Here, we were very off with the uncertainty. What? Oh, right. The star is very small. It is actually right here. Very small. That is what we would have had to look at to find the transit.
All right, so the second candidate we caught was TOI 5278, which also had promising results because its depth was 119 millimag. Basically, 11% of the star was going to be, of the star's light was going to be lost, so it would be a very interesting candidate. And just like the previous one, the period is super short, and the magnitude wasn't all too bad as well. So it was a really good, promising candidate. And as you can see here, we ended up catching the transit. But since the magnitude is 14.9, it's also a very faint star. So does anyone want to guess which star it is? Anyone? Okay, sorry. Does anyone want to guess which star we observed in the image? Does anyone? No, right. Okay, not the really bright one. Actually, it's this one right there in the middle. Super faint. So, yeah, all right. We good?
So back to midpoint uncertainty. Like TOI 5848, we couldn't catch a transit, and that is because we had a 50% midpoint uncertainty. Let me explain a little bit what midpoint uncertainty is. So when we observe an exoplanet, we only observe it for a certain amount of time, and we're not always observing it. So there's always a little bit of an uncertainty or an error as to when that planet would transit. As you can see in the graph here, there are points where you can see where the transit is. The y-axis is the number of transits, and the x-axis is the time when that planet transits. If you have a very few number of transits, you will see that the error, which is the uncertainty, will grow for a time where you do not observe it for a while. So let's say you had an observation a year ago. The uncertainty would have grown by so much that we won't know exactly when that planet will transit, which is a reason as to why we need to observe every so often. You can see that the blue and red lines are widening, which means that the error is growing. So, concluding thoughts, even though TOI 5848, we didn't catch a transit for it, we can now narrow that down to a smaller midpoint uncertainty, helping us potentially catch it next time. For TOI 5278, we can potentially publish our findings for confirming it as an exoplanet. Thank you. Any questions? We want to... Any questions?
What telescopes with the Untitled network do you guys use to collect your data?
Could you repeat the question, please?
So the question was, what telescopes and the LCO do we use? We use a number of telescopes, potentially, we use the Haleakala one. I also think for other observations we use Mauna Kea, but yeah.
Maybe the 2 meter?
I think the 1 meter, yeah. Never mind, it was a 40 centimeter. Never mind, it was the 2 meter.
That one was my bad. Okay, it was my mistake. It was the 2 meter.
Any other questions?
So when you see a planet transiting, you mentioned that it is dimming, and then you figure out that it probably, again, this now to say a few months.
Right.
How do you know it's the same planet and not something else?
Well, we observe it a few times, and if the period is the same, then we can determine that it's probably the same planet. Yeah, and the depth of the transit. Because if the planet's a certain size relative to the star, the transit depth will be equivalent in all the observations. The transit depth, how much of the light the planet blocked from the star, be the same. Yeah, use a period for Kepler's laws. There's an equation, and you can use the Earth and Sun relevance to compare that to other systems, and you can determine the period and also the distance between the planet and the star. You guys want to take it? You want to take it? You want to take the question?
So you asked why we chose exoplanets. For me personally, I just find it really cool that there are other like celestial bodies that are orbiting other stars, because like we don't know what they are. What if they have water or life on it? It's like really cool.
I'd like to add something. At the beginning of this program, we were given a question: what would we like to do our project on? I answered, I would like to discover something. And so I'd say with this project, we discovered something. We have really, we found what appears to be an exoplanet. So we have the ability now to continue observing TOI 5278 and potentially write a paper and publish and confirm TOI 5278 as a confirmed planet.
Let's thank our exoplanet group one more time.
All right. Well, thank you very much, everyone. Tyler, to get back to your question about which telescope they used, it turns out that was a bit of a trick question for them. They used the 2 meter, they used a 1 meter, and they used a 0.4 meter. Technically 35 centimeter, I know. So they used all sizes of telescopes on the Los Cumbres network. We want to say thank you to a few people. Let's first of all thank our brilliant MC, Mr. Mike Nassir. Yes.
And in case she's listening, I want to thank our colleague who founded the High Star program with us, Mary Kataoka. She was with the program for the first decade plus, and so in case you're out there listening, thank you very much. She's now enjoying her second retirement from her retirement, finally at last, so thanks.
I wouldn't call it a retirement at this point. I would call it maybe graduation until she moves on to the next thing. Yes, Mary Kataoka is very enthusiastic, very energetic. We also wanted to say thank you to the mentors, Willem Hoggendam. Go ahead and stand up in the audience back there. And Miranda Kong. Brilliant work. We also wanted to say thank you to Carolyn Kaichi, who has been keeping everything running behind the scenes flawlessly and we really appreciate that. She's actually retiring, which is just devastating to us. What? Graduating. She's graduating, which is devastating to us. Thank you to Dr. Larry Harrison, who is with the University of Hawaii Maui College, and to UH Maui College for hosting this. We also want to say thank you to Los Cumbres, in addition to providing telescope time for the High Star students. They also have been supporting it financially, which we couldn't survive without the financial support of them. And Space Force, Air Force Office of Scientific Research, has been supporting the program as well. So thank you to both of them. Am I forgetting someone? I'm probably forgetting someone, and I feel really bad. Yes?
During the
class. Yes. Miranda, yeah, yeah. I'll say it again. So Miranda Kong, is that, yes. Miranda Kong was the Galaxies group mentor. Yes, and okay, am I forgetting anyone else this time? All right.
Before we sign off, there have been many other grad student mentors, faculty mentors over the years, and host locations. And so just thank you very much for keeping High Star going for, wow, it's almost 2 decades.
Over
right?
2 decades.
It's
2007
almost. It's almost.
would be 2 decades.
It'll be almost. So
No,
anyway,
it
but it's
would
not
be-
possible without a lot of different people and sustained efforts. So lots of mahalos. Thank you.
It started in 2007, so this is year 20. So I would, so you might count that as 2 decades. Okay. All right, yes, okay. All right, thank you, and then we'll sign off here.
Thanks for coming, everyone.